Hi, welcome to Section 6.1 Notes. This is on the polygon angle sum theorems. So a polygon is a many-sided closed figure formed by a finite number of sides. So here's some examples. So a polygon, a triangle, a hexagon, heptagon, all of those are polygons. Any shape made up of straight edges, and it can have any number of sides, but it must be closed. So the difference between a convex and a concave polygon, a convex polygon you can see here is a polygon for which any two interior parts can be connected by a line segment that stays entirely inside the polygon. So you can see here, any two parts of this polygon that I try to connect, all of these lines are completely within the figure. Where a concave polygon, I think of it as it's caved in, and you can see that right here, that a concave polygon is a polygon for which a line segment may pass outside the figure from two interior parts. So you can see here they made this line. They're connecting two parts of the figure, but that line goes in outside the figure since it's caved in. So those are just words to be familiar with. So here's some different types of polygons. So the first one we have here, because of all these congruent markings on the figure, then we would consider this an equilateral polygon. Okay, and again, the reason is because all sides are congruent. Okay, this next one is a equiangular polygon. Because all the angles are congruent. And this last one is a regular polygon. And that's the term they're going to refer to the most. And it is one that has all sides and all angles congruent. Okay, so it's equiangular and equilateral, and that's what makes it a regular polygon. So they don't have to have all those markings. If they just say in the problem that it's a regular polygon, then you know that all the sides and all the angles are congruent. Okay, the interior angle sum theorem says if a polygon has n sides and capital S is the sum of the measure of its interior angles, then our formula is 180 times n minus 2. Okay, where I'm going to write in here what these stand for. The S stands for the sum of the interior angles, and the N stands for the number of sides, which is actually what it says off to the right here. Okay, S is the sum of the interior or inside angles, and N is the number of sides. So we can use this formula. Let me move it up a little bit. We can use this formula to solve. So example 1 says if a polygon has 15 sides, what is the sum of its interior angles? So I just like to write the formula that I'm going to use every time. And then I can do the work to solve it. So the N in this case is 15 sides, because that's how many sides the figure has. But then the rest of the formula stays the same. And so now if I solve that using the right order of operations, I'm going to do what's in the parentheses first, which is 13. 15 minus 2 is 13. Now if I just multiply 180 times 13, I get 2,340. So some of these numbers are going to get kind of big because you have to think about if it has a lot of sides, there's a lot of obtuse open angles. And so those angles are going to add up pretty quickly. And that's my answer there. Example 2 says if the sum of the polygon's interior angles is 900, how many sides does it have? So just pay attention to what it's giving you and what they're asking you to find. In this case, they're telling me that the S is 900. And this time they're asking me for what is the N. So I can still write down my formula. But plug in what you know and solve. That's a question mark. Solve for what you don't know. So here's my 900. And then n is the thing that I don't know. So again, you just have to use the right order of operations to solve. You can do anything you want to an equation as long as you do the same thing to both sides. So the quickest thing I see to do, you could distribute the 180 through to be able to solve for n. But the quickest way I see to solve this is I can divide both sides by 180, okay, to get rid of it. So if I do that, 900 divided by 180 gives me 5. The 180 over 180 cancels out to be 1. And I'm left over here with n minus 2. Now I'm really close to being done. I can go and add 2 to both sides. And off to the side here, I'll put that I end up with 7 is equal to n. So I know that the figure has 7 sides. If you think about what a 7-side figure is, it is a heptagon. So that's something we'll review over in a few minutes. All right, next says, example 3, what is the measuring a y in pentagon today? So a pentagon is a 5-sided figure, and that's what this figure is. And they want me to figure out what this angle y is, which is right here. That's our question mark. So if I write down my formula, S equals 180 times n minus 2, the sum of the interior angles, I actually know some of them this time, so I'm going to add them up. I'm going to say 110 plus 90, that's what the symbol means, plus 120 plus 150 plus the measure angle y. If you want to put an x or something in there, that's fine. And that's equal to what I have on the other side of my equation is 180 times n. I know what that is because I can count 1, 2, 3, 4, 5 for the sides of the figure. And 5 minus 2 is still part of the problem. So if I go and add up all these angles I know, I get 470 plus the measure of angle y that I don't know that I'm trying to find is equal to 180 times 3, because that's what 5 minus 2 is. Now I've got 470 plus the measure of angle y is equal to 180 times 3, which is 540. From there, if I go and subtract 470 from both sides, then I am left with the measure of angle y is equal to 70 degrees. Because I did 540 minus 470 and got 70. So that's a way to use the formula to find out a missing angle. Okay. The next one is very, very similar to what we just did. So that would be a good one for you to practice. I would pause the video and go ahead and try that one. And then when you come back, you can check to see if you did that right. Okay, so welcome back. I'm going to go ahead and work through it now. I'm still using this formula. This time it says it's a quadrilateral, and angle G is what I don't know, but everything else is the same. So the sum of the interior angles is the 120 plus 85 plus 53 plus measure of angle G that I don't know is equal to 180 times n. They didn't tell me n, but I can look at the picture and see that it has 4 sides. So 4 and then minus 2 is still part of the formula. So if I go and add up the angles I do know, I get 258 plus measure of angle G is equal to 180 times 2. So I get 258 plus measure of angle G is equal to 360. And now if I go and subtract 258 from both sides, kind of running out of room here. So 258, then I end up with the measure of angle G is equal to 360 minus 258, which is 102. And a way you can check yourself is if you remember that a quadrilateral, that all the angles add up to 360, then you can add up all these inside angles, interior angles, and make sure it gives you that. Okay, if you look at example 5, it says find the measure of each angle. Really, we're doing the same thing we've just been doing. It just looks a little different because all the angles have x's in them, but it's still the same idea. So I still want to use my S equals 180 times n minus 2 formula. I'm still going to add up these interior angles, just looks a little different. So it's 2x plus 2x plus x plus x is equal to 180. Now for the n, I know the figure has 4 sides, minus 2. So that part's the same as what we did a minute ago. If I add up all my x's, 2x plus 2x plus x plus x, I have 6x. This 180 times 4 minus 2 is the same as what we had up above, which ended up giving us 360. So I'm going to go and write 360. And then if I go and divide by 6 on both sides, then I end up with x is equal to 60. Okay, but that's not what the question's asking. The question asks, what's the measure of angle A? Well, since x is 60, I know angle A is 60. Angle B is actually 2x, which is 2 times 60, so that gives me 120. Okay, angle C is actually 2x, which is 2 times 60, which is 120. And angle D is just x, so I know that's 60. And if you want to double check that all of those add up to 360, then that will help you verify that. All right, on section 6.2, or theorem 6.2, the polygon exterior angle sum theorem says that the sum of the measures of the exterior angles of a polygon, one at each vertex, is 360. So this one's a little different because the sum of the interior angles changes depending on how many sides the figure has. The sum of the exterior angles is always, always, always 360. If you want to write that down, sum of exterior angles of any polygon equals 360. Okay, so that's basically what it's saying here, but I just want to make sure you realize any polygon, it doesn't matter if it's a triangle or a quadrilateral or a pentagon or a hexagon or whatever, all the exterior angles, remember exterior is if you extend out one of the sides, that is an exterior angle. So we're saying that all of these angles that are on the outside of the figure are always going to add up to 360 no matter how many there are. It just means the more sides the figure has, the more exterior angles they have, and so the exterior angles get smaller and smaller the more the sides there are. So the other thing that I was going to write in here is that all of the exterior angles are congruent if it's a regular polygon. And remember, we said a regular polygon has all the sides and angles congruent to each other. So if that's the case, then all the exterior angles would add up to 360, but also all the exterior angles would be congruent to each other. So in example 6, it says, find the exterior angle of measure 1 in the regular octagon. So regular meaning all the sides and angles are congruent, even though they didn't mark it. So therefore, all the exterior angles are congruent. And octagon meaning it has 8 sides. So if I know that the sum of the exterior angles is 360, and I know that I have 8 exterior angles, I can just go 360 divided by 8 to get 45 degrees. Okay, and again, this regular part means all sides and angles congruent. If you need to write a little reminder there. Okay, next. It says on 7, what is the sum of the interior angle measures of an 11-gon? So it's asking not just what one interior angle is, it's asking for the sum of the interior angles. So we have a formula for that. that we've already used a few times. So if they're asking for the sum, and I know the measure, an 11gon is just an 11-sided figure. They just don't have a special name for it. So I'm going to put 11 in for the ends place. And now I just need to solve from there. Sometimes there's more than one way you can get an answer. So there is another way I could do it. But to me, this is the easiest way to get the sum of the interior angles. So 11 minus 2 is 9. And if I go and multiply those, I get 1,620 degrees for the sum of the interior angles. Again, just pay attention if they're asking for the sum of the interior angles or just one interior angle, because there's a difference. Example 8 says, what is the measure of an exterior angle? So here it's not saying what is the sum of the exterior angles, which we know would be 360. We want to know what just one is. It is telling me it's a regular polygon, and we can see the polygon is a 15gon, so it has 15 sides. So to get the exterior angle, I know the sum is 360. I can divide that by how many sides the figure has, which is also how many exterior angles it has. And if I do that, I end up with 24 degrees. And so each of those exterior angles is going to be 24 degrees. All right, last one on this page says find the measures of an interior angle and an exterior angle of a regular decagon. So again, that's asking for one interior angle and one exterior angle. And they are telling me it's a regular polygon, so all the sides and angles are congruent. And then it's telling me here that it's a decagon, which means it has 10 sides. So you have to kind of think through that. So different ways I could do this. The quickest way, I think, to do it is to think that the exterior angle, that I know the sum of the exterior angles is 360. I know there's 10 sides of this figure. And so I know that the exterior angle is equal to 36 degrees. That's what one of them is. So that answers one part of the question. The other thing that I know is that an interior angle, you can actually see if you look up here. If you look up here, kind of at the top of the screen right now, see how there's an exterior angle and an interior angle right beside each other? If you think back to chapter 1, think how many degrees do those two add up to? And it's 180. Okay, one interior and one exterior angle forms a straight line because an exterior angle is basically just an extension of one of those sides. So they are a linear pair. They add up to 180. So if I know what one exterior angle is, then I know the interior angle is 180 minus whatever the exterior angle is. So in this case, I get the interior angle is 144 degrees. Okay. All right, so that's the main part of the notes for section 6.1. But we're going to go ahead and do these other two pages because I think it's just going to help reinforce some of this and kind of give you a little review. So I'm moving backwards here. But we should be able to go through it pretty quickly because you're already familiar with some of it. And then I think that last page is going to help give you some reminders that you need to know. So again, a polygon is a closed figure formed by a finite number of sides. A convex polygon is a polygon for which there is no line that contains both a side of the polygon and a point in the interior of the polygon. So we said an example is something like that, where a concave polygon is caved in somewhere. And an equilateral polygon is a polygon with all sides congruent. And an equiangular polygon has all angles congruent. And a regular polygon is a convex polygon in which all of the sides and all of the angles are so all the sides and all the angles are congruent. It's a regular polygon. Okay, so now just a little review over some of the formulas. The interior angle sum theorem is that S is equal to 180 times n minus 2. Okay, we talked a lot about that. The exterior angle sum theorem is that the sum of the exterior angles of any polygon, and I mean any, is equal to 360. Okay, now to get the measure of one interior angle, you can, two different ways to do it. The way we just did it a minute ago is you could just subtract from the exterior angle. If you know the exterior angle, you can just do 180 minus the exterior angle to get the interior angle. The other way that you can do it is you can find the sum of the interior angles, which is the 180 times n minus 2. That gives you what all the interior angles are added up. And then you can divide that by how many sides and therefore how many angles there are, and that will give you what one is. So that's one way. But the other way, again, is just subtract from 180 from what the exterior angle is. To get one exterior angle, you can just do 360 divided by n, which is how many sides it has, and therefore how many exterior angles it has. And the one extra thing that I'm going to add here is that one interior angle plus one exterior angle is equal to 180. So sometimes there's more than one way you can do something, and that's one way to do it. If you know one of those, you can subtract from 180 to get the other one. All right, so a couple things down here. What does n represent? We've said this multiple times. It's the number of sides. What must we know about a polygon in order to use the formulas to find the measure of each interior angle and or each exterior angle of a polygon? We must know the number of sides, and it must be a regular polygon to do it that way. Okay, and what is another relationship that we can use to help find missing interior or exterior angles in any polygon if we already know one interior or one exterior angle? Other than the formula, and like we were just talking about, we could subtract from 180, and that's because they form a linear pair. So we know they are supplementary. All right, you're doing great. Last page. Here we go. So we can go through this pretty quickly. I know it looks like a lot of boxes, but in this particular case, then finding mine. For the first thing, it's kind of like a chart that's going to give us some good reminders and kind of see where some of these formulas and things are coming from. So the first row is asking us how many sides these figures have, and you can see the figures right above. So if you don't know, you can just count how many sides, and you should see a pattern here. So we can see that a triangle has 3 sides, a quadrilateral has 4 sides, a pentagon has 5 sides, a hexagon has 6 sides, a heptagon has 7, octagon has 8 sides, nonagon has 9 sides, decagon has 10 sides, and then an n-gon is just, they don't have a name for it, but they just might say 15-gon or something. So we'll just say it has n sides. So on the next row, but you do need to be familiar with these. From 3 up to 10, you should know how many sides it has when that's mentioned. So now it's asking for the number of triangles created. So I'll show you what I mean in just a second. But if I look at the first triangle, there's just one triangle in that picture. In the second one, if I connect 2 of the vertices, you can see I end up with 2 triangles in that figure. If I start at a vertex and connect some lines on this one, you can see I end up with 3 triangles in that picture for the pentagon. For the hexagon, you can see I have 3 lines, but that ends up with 4 triangles. For the heptagon, you can see it looks a little messy, but I end up with 5 triangles. Okay, I think you see the pattern. If I keep going, I get 6, 7, 8. It's just harder to draw the more there are. So if I think of what's going on here, all of these numbers are 2 less than the one above it. So whatever n is, then the number of triangles created is n minus 2. Okay, next thing it says is the sum of the interior angles in a triangle. That's something we learned in chapter 1 in geometry, and that's 180. All the angles of a triangle add up to 180. So that's what we're putting here. Okay, and now if the sum of the interior angles of a polygon is, I can just multiply these two blue ones. 1 times 180, because there's only one triangle, I get 180. 2 times 180 means that for a quadrilateral, the angles add up to 360. 3 times 180 means for a pentagon that they add up to 540. I should have degree symbols with these. 4 times 180 gives me 720 for a hexagon. 5 times 180 is 900 for a heptagon. 6 times 180 is 1080 for an octagon. 7 times 180 is 1260. And 8 times 180 is 1440. And the n minus 2 times 180 is, like we've just been talking about with the formula. That's what the sum of the interior angles represents. Okay. If we look down at the next part, it says sum of all the interior angles. So those numbers we just got up above, I can write down here. And then we're going to do something else with them. Okay, now it says the number of angles. Okay, so in this case, the number of angles, I guess it should have said interior angles in that figure is there's 3 for a triangle. For a quadrilateral, there's 4. And I'm going to go ahead and erase my blue lines up here so you can look at these figures and see how many angles it has. Basically, the number of angles is the same as the number of sides. So it's basically that top row of red that I have up there. How many sides it has is how many interior angles it has. Okay. And then what we're going to do here, if we know what all the interior angles are, and we want to know just what, you can see what this next row says, measure of each interior angle, just what one is, then we're technically dividing these to get that answer. Where up here we multiplied, like 1 times 180 to get the answer, 2 times 180, 3 times 180, 4 times 180, and so forth. That's what we were doing. We were multiplying these two to get that bottom. We're up down here, we're actually dividing to get what the next row is. So each interior angle in this case is going to be 180 divided by 3 for a triangle is 60. 360 divided by 4 gives me 90 for a quadrilateral. 540 divided by 5 is 108. And again, if you keep dividing, you'll see I end up with 120. I end up with 128.57. For the heptagon, I end up with 135. So not all of them end up being whole numbers. For a nonagon, a 9-sided figure, I end up with 140. For a decagon, I end up with 144. And so my formula here is for one interior angle is 180 times n minus 2, all divided by n. And we wrote that on the other side a minute ago. Okay, last little bit here is talking about the sum of the exterior angles. So we can't quite see everything, but we can see a lot of it. So in this case, the sum of the exterior angles we talked about is going to be 360 for any polygon. So I'm just going 360 all the way across. And it doesn't matter how many sides it has. And now, again, the number of angles. So the number of sides of the figure is the same as the number of interior angles, which is the same as the number of exterior angles. So in this case, a triangle has 3 sides, quadrilateral has 4, pentagon has 5, hexagon 6, heptagon 7, octagon 8, nonagon 9, decagon 10, n-gon n. And so again, what I'm going to do with these numbers is I'm going to divide. And that's going to tell me what one exterior angle is. So just need to write that and then we'll be done. So 360 divided by 3 is 120. Quadrilateral is going to have 90 degrees for each of the exterior angles. Pentagon's going to have 72 degrees. Hexagon's going to have 60. You can see they're getting smaller and smaller. Heptagon is 51.43 degrees. Now, octagon has 45 degrees, and nonagon has 40 degrees. Decagon has 36. And so just a regular n-gon is 360 divided by n. So you can see they keep getting smaller and smaller. So like if the figure had 22 sides or 32 sides or 40 sides, again, it's going to keep getting smaller. It's never going to get to 0, but it's going to get really, really close to 0 the more sides it has. Technically, the more sides it has, the closer it's becoming to a circle. So that is all for section 6.1. Thanks for joining in, and let me know if you have any questions.